No sé, computer. Okay. Everybody's done? Can we start? Okay. So hello everyone. And okay, so we're gonna shift gear in our class.
from EEG. That was the first section. Now we're going to move to MRI, which is the main section of this class. Also the main method, I guess, for researching the human brain. And the way we're gonna do it is we're gonna look first. This class is gonna be really kind of understanding the machine, the physics. I'm apologizing early. It's a little bit. Some people find this part hard in an earlier year. I try to make it easier this year. I hope it will be easier. There will be also the practice, which actually not going to focus on that, because this is kind of the background for the next thing that we actually care about, which is then how we're using the MRI first to research brain anatomy, brain structure. That will be the next two classes. And then we're going to go for functional MRI, so how we measure function with it. And there, we're first going to, well, we have time, but it will be first how it's related to the signal, and then we're going to go to how it's actually been used in fMRI. So that's the plan for the rest of the year or the semester. So MRI, and so that's going to be an introduction to MRI. I already mentioned that. Well, it's the best and probably it's stretched to there. It's the main tool we have to look inside the brain without opening the brain, right? And that's very useful for humans, and it allows us to image, in this case, brain structure. So here you see different slices and the 3D image of a brain. And it's something we're doing routinely in the clinic, but also in research. But there's other ways to look at the brain, and it's actually a wonderful machine. There's not one thing you can do with it. It's different things you can do with it, and we're going to understand what is these different things that we can do. And we're going to get different information. If this one was structure, this different type of structure in which we can image white matter pathways, so looking on orientation, or we can look on blood vessels. So another contrast will allow us to look on blood vessels in the brain, and other method would allow us to map functional function, so fMRI. And there are more. I just give you the idea is that there are many types of MRIs, and which can allow us to measure different types of information. And MRI as a system is a very complex system. I actually think that there is no one MRI researcher that actually understands it fully. In many ways, like this babushka, I don't know how you call it in English actually. Babushka? When there is the physics, and then there is the engineering, and then there is there is different manipulation in how you do the measurement, and then how you register the image from a lot of CS, and then there is the biological interpretation, and there is the cognitive interpretation. There are many layers, and it's typically the case that someone is really good in one, and it's rare that people actually fully understand it from the beginning to the end, or how would you use it for cognitive research and being also really understand the physics very well. Some of them wouldn't know it, and sometimes that also raises critiques of users. You don't understand your machine, others say, oh, but you don't know what to do with it. So you will get a taste of that. There is many layers to that, and I would like you to be at least as you read the research, and you're probably going to read. Let's say you're not continuing this field, but you're just going to read sometime the research, and they might use fMRI or tractography, diffusion. At least what I want you is to be able to understand at least vaguely what was the measurement, what was maybe the priors. So that's the idea of this class, to give you a sense so you won't be, like many people who actually use fMRI, I don't want you to be totally ignorant about what is this machine and how they got these images in the end. Okay, so that's if we get there and you feel like more comfortable with such articles, then then it's a success. So let's try. So what is MRI? It's a huge magnet. Okay. So typically, it's like a big tube. Is anyone here who never saw an MRI? Everybody been inside an MRI? You haven't been. So you're all welcome to come and visit our MRI. We have MRI in LSEC. And if you want to just see how we're doing experiment, you can chat with Shai. She will tell you when we're scanning, and we can come and visit. You can do it also organized. A year before we actually did an organized tour to there. You can think about it as well. Anyway, it's a big tube essentially that the subject lies inside. So there is a bed, and he lies inside the bed, and all these things have a constant, very high magnetic field. We're going to discuss how it happens exactly. And there are other instruments that comes with that. So we're going to call it magnet or scanner, okay? And this scanner has different gradients. Those gradients will create a perturbation in the magnetic field. I will explain it more, but around this, the subject beside the magnetic field, there's also other machines that allow perturbation in this magnetic field. And we're also going to transmit something to the subject, some energy. And the nice thing about MRI is that the energy is radio frequency, so it's essentially it's fine to be scanned. There is no real danger to be exposed to radio frequency. We're exposed to radio frequency all the time, right? In our cell phones, for instance. So radio frequency is fine. And so that's why it's safe and very useful method for in vivo scanning. What also we have in the MR scanner behind us, so there's the control room. So there's the scanner there up there. Oh, can I get there? No. I will bring the pointer to the next part. We have also a huge machine room in the back. If you go to the scanner, you hear a very noisy room with many computers and other machines. And there is a constant room when we actually the researchers sit and interact with the subject inside the magnet. And there is a full infrastructure also to take the information from the magnet, convert it to images, and essentially aggregate that. It creates a big data set, and there is a full system to handle that. Okay, it's very basic. It's important to notice that I mentioned that already. There are those gradients around the subject in this tube. Okay, so it's a gradient. I will explain what I mean by gradient in a second. And they're defined as x, y, and z gradient. And if I say x, y, and z, what do you think it might be used to? Direction of? Field. So it's going to create some kind of perturbation of the field in x, y, z, and that might be useful for something about space, find location. So we're going to make images. We're not going to make a single measurement in MRI. We're going to make a measurement of an image or maybe a volume. And so we need a way to create some kind of variability in the magnetic field in space. So if we won't do that, that's become an NMR. Some of you maybe learned in chemistry or physics. There is a machine, NMR, very useful. Here we're doing NMR, but as an image, and only for protons, only for one type of atom. We're going to talk about it in a second. And this gradient is going to create some perturbation in the magnetic field that would allow us to make an image, okay, of volume. So that's why it's used. That's what it's used for. And yeah, gradients. Okay, so let's talk for a second about the phenomena. I hope all of you learned something about magnetic field in physics, maybe in high school or something like that. You know that I assume that all of you know that if we have an electric current, there will be a perpendicular magnetic field to it, right? So if we'll have some kind of a circle which have inside it electric current, there will be a magnetic field that is perpendicular to that. Yeah, that's okay for everyone. We don't need much more than that. And so, and we have units to describe this magnetic field. It's either Gauss or Tesla, which both were a very famous researcher, which also were researching electricity and magnetic phenomena, and it's named by them. So the typical magnetic field of Earth, for instance, is about half Gauss. Okay, so that's the size. And if you would go around your refrigerator, it's going to be 200 Gauss. And if you go to an MRI machine, it will be something between 15,000 Gauss to 90,000 Gauss. It's a huge magnetic field. So not a magnetic field that we experience in our daily life. That's very important to know. We're creating an environment which have a huge magnetic field. Okay? We call 10,000 Gauss a Tesla. So we're typically going to say I have a magnet of 1.5 Tesla, 3 Tesla. You might hear those names. We have a 3 Tesla in here. And now, the Weizmann Institute with other university bought a new human MRI, 7 Tesla. Much bigger. We're going to talk about why it's important. But typically what we see in a hospital and in research center is going to be either 1.5 or 3 Tesla. The 7 Tesla is unique, for instance. For animals, by the way, we can use higher magnetic field. Okay. So an important thing about this magnetic field that is, we're going to create a magnetic field that will penetrate, if you want, the center of the magnet. We're going to call it the Z direction. This is the field of the magnetic field that goes through the magnet, okay? And it's a constant magnetic field or magnetic flux. We can also define that. We might call it B0, that just go inside the magnet. So when the subject lies inside or the head is inside, the magnetic field, if you want the main line of the magnetic field, just go through him, through the brain, and pointing out. Okay? And it's important to know that it's a constant magnetic field. It's always there. I will just just tell you that the problem, it's actually a problem that it's always there, because something we forget. What happens if you come with a metal to a magnetic field? What do you think would happen? If you come with a metal to a magnetic field? It will fly. It will fly and will fly like a bullet. So that's the main risk in MRI, actually, to the machine and to the subject, if there is a subject. And in the early days, there was some instance when people came, for instance, mainly in the hospitals, when they went with, let's say, it's like a air balloon or a CO2 or O2, like a big balloons which are metal, just fly into the magnet, and there are people who died because of that. That's rare. Currently, it's very rare that those things happen, but we should be always cautious, and we are trying to be always cautious. That's the main risk in MRI, metals. Anyway, so how we can make a uniform, constant magnetic field inside a magnet to create our magnet, essentially. So we need these metal wires. We need at least 2 to create a magnetic field. But it will be pretty small. So what we need to do in order to get a big and uniform magnetic field, big enough to fill the whole body, we typically don't use just a head MRI. We fill with a body MRI, which have like a diameter for bigger men than me. So we typically have many wires like that goes around, and we inject the current inside, and then we can create this uniform magnetic field. Now, you might think that we're constantly injecting tons of current inside. So like there is a huge demand of electricity in a magnet in order to create this huge magnetic field. The reality is that we're actually not doing it in that way. The way we're doing it is we're using materials we call superconductors. Maybe you heard about it, maybe you don't. They don't have any, when they are cold, really cold, close to 0 Kelvin, super cold, they are superconductors, and they don't have almost no resistance or 0 resistance. And then you inject the current once, this huge current, you keep it very cool, always, seal it, keep it very cool, and then you have constant magnetic field in the magnet. So that's why I say it's constant, it's always there. There is no noise for that, and there is no, like, we don't always pumping a huge, we don't take from the electrical grid tons of electricity all the time. We did it once. What we are paying all the time is for keeping it cool. So there is a full machine that use either liquid helium or other materials, which condensing helium allows to really cool the system to be close to 0 Kelvin. If you've been in a magnet, you will hear this like whoosh, 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 whoosh. Like the scanner is breathing. It's actually the machine that's condensing the helium that's doing this noise. And sometimes when these things actually, so that's another risk in MRI. If by any case this helium penetrates to the room, it will take all the oxygen out, and you can stay without oxygen. And of course, so that's another potential risk in MRI, much rarer than getting inside with metals, but that's part of the system. So it's really high condensed liquid helium that we have there, and should stay close and safe. Okay, So the magnetic field is magnetic field, that's it. We don't play with it, we don't change it. We hope it's uniform. It's almost uniform. There is imperfection, but yeah, you inject the current once, you check it every time. So every day we check that everything is okay. But assuming nothing happened, we don't play with it. There is a constant magnetic field around 3 Tesla, about uniform, and that's it. So as a user, you don't care. You just need the company to come and check that everything is fine, and there is no problem with cooling and no problem. But something that we don't play with. We play with something else. You will see in a second. But let's talk about what we're actually measuring. Well, okay, fine. We have a huge magnetic field. What are we going to do with that? What we are measuring? Does anyone know what we are measuring? Maybe you heard about it in the lecture. What is the material that we can measure? Hydrogen. And what about this hydrogen? So the proton. What about those protons? They have a spin. So there's some kind of magnetic phenomena. It's a quantum physics phenomena, but it can be translated to a moment, to a magnetic moment. So it's like a small magnet, right? And we have many of those. And inside magnetic field, they will actually care if they are aligned or not aligned to the magnetic field. So that's going to be our signal. That's where the signal is going to come from. Okay? So just let's talk about this moment phenomena. Different particle has it. In this case, it's an electron, but also proton and neutron has it. In MRI, we're only going to talk about protons. There are some attempts to do what's called MRS, so looking on other particles, other atoms, not other particles, beside MRI. Other particles people are doing, but not as a method to image brain, so I'm not going to talk about it at all. But let's start with the common thing. We typically, so we have these protons inside the atom. Do you remember it from chemistry? There is an atom, they have electrons, and then there is the nucleus, right? It's magnetic nuclear resonance. So inside the nucleus, there's protons and neutrons, right? And in general, both of them have spins. And so what we need a case, a nuclear which doesn't have an even numbers of protons and neutrons. So the net effect of this atom will be if each of them have some spins, have some kind of magnetic moment, they might cancel each other unless we have uneven number, and then we'll stay with a magnetic moment of this nucleus. Okay? And so proton is a case in which there is only proton. There is no neutron in this. It's the simplest nucleus that exists in nature, and it also have one. It's simple. That's nice. It's very abundant. We're going to talk about it in a second, right? We fill with water and we have hydrogen all over us, and it has magnetic moment. All of that make it the thing that we're going to use for our measurement. So, yes. So for instance, in water we have 2 hydrogens, so 2 protons. Each of them have spin of half. Okay, so they have a spin, and because they have this number. Do you remember it from the table, right? Each atom had a number. Often, for instance, it's 16, and in this nucleus it's cancelled out, and we don't have any magnetic phenomena that we can measure. We can create an isotope of oxygen, and then we'll be able to measure it. And people actually try to do that with carbon. Carbon 12 doesn't have a magnetic moment that we can measure, but carbon 13, which is an isotope that exists, and we can actually enrich it in the food, for instance. And then people try to measure it. That's a big thing that's now happening in MRI. We're not going to discuss it more. Okay. But spin. Proton have a spin of a half, and inside us there is many protons. It's the most abundant nuclear. Actually, this is the number in the whole body. So it's a very abundant thing. And if we look on the spin phenomena when there is no magnetic field, or there is very weak magnetic field, like in Earth right now, then nothing happened. They don't sum up to nothing, and they don't choose it. There is no preference orientation because the magnetic field is too small, and it just doesn't make any effect. But when we put all those spins inside a very strong magnetic field, then some of them, they will start to align along the magnetic field. Like if you put a needle near a magnet, it's kind of like want to orient it itself to the magnetic field. Okay, so kind of using this intuition, you can think about these proton spins that now start to align toward the magnetic field. So this is going to be the B0. Okay, and we sum them, and we're starting to get a vector, a magnetic vector. And this phenomena is a quantum phenomena, and I'm kind of did the hand wavy explanation. The summary of that, creating a vector, a magnetic vector, it's already a non-quantum. We can explain that and work with it as a classic physics phenomena vector, magnetic vector that we're gonna play with. So everybody got it that we got now a magnetic vector. Just that for now. Okay, we sum them all. They all orient themselves. Not all is wrong here, but enough. Orient them for more. There is a preference to be oriented to the B0 field in a way that actually generates a magnetic vector. Okay. So here it is again. We have a magnetic vector that is oriented toward the z direction. That's the B0 direction. Okay. So there is x, y, and z is always the main magnetic field direction. And just more for the intuition, what happened in the magnetic field? There was here is again some kind of a quantum mechanic hand wavy explanation, really hand wavy. There is what happened here is that there are two levels of energy being parallel and anti-parallel to the magnetic field. Okay, and one of them have higher energy than the other. Okay, so one is more preferred and the other one is less. Okay, and there is a jump between them, in which have some kind of level of energy. And so what I'm going to do, the experiment in general is that they want to be in one orientation. There is more of them that will be in one orientation versus the other, and I will going to transmit energy exactly in this jump of energy. Okay, there will be some frequency of energy that I will need to push to the system. That will be the radio frequency. That's gonna take some of those protons that were in the preferable orientation and flip them. So now the magnetic vector will be summed in a different way. I will show you that all in details, and then it will come back. So there's excitation and relaxation, like in many other methods that you might learn or learning now. In the other method course, right? So many times we do perturbation, take the system out of steady state, and then it go back to its steady state position. Are you okay? Are you with me? There was two levels of energy. We took it out we push some energy in. We take it out of its steady state, and then it go back. And so that will be the phenomena. And while we're doing that, we'll be able to measure the signal, and that will be our signal. That will be the phenomena that we're going to measure. Okay? So, but for now, there are two levels of energy, and there will be a more proton in one orientation versus the other, and we're going to perturbate that and see what happens after. That's the basic thought. And so those levels of energy, these two levels of energy, which sometimes also called the Larmor frequency, and it has to do with the frequency that this spin actually, and I'm going to say something more, this vector is actually is moving around the main magnetic field called precession, this phenomenon of precession, which have a frequency. Okay, so and the level of energy is changing according to the magnetic field that I'm using. So in Earth magnetic field, it's kind of here. There is no difference between the two levels of energy, so that's why I have no signal. But as I'm increasing the magnetic field, there is enough delta energy that they actually would prefer one orientation, and I can also add energy, make them jump to one level versus the other, and then they will go back. Okay, so we have a way to perturbate the system. Okay, so the way to describe this dependency is according to this Larmor frequency, and this is just a linear function which relate the magnetic field with some constant, which is the gyromagnetic constant, and then we have a different magnet with different Tesla. We have a different typical frequency in which those protons will will process, okay, and that's also the energy that I will going to insert inside. And what is interesting is that those energies are in the megahertz, so that's why it's so useful. We're going to play here with energies which are in radio frequency, so that's what makes it non-invasive, not causing any harm. Okay, this energy that as a tissue we can inject a lot before we're actually heating anything, and it's fine. Okay. So in the beginning of our experiment, we have this vector of spin that projects toward the z direction, and as I'm injecting this radio frequency, I'm flipping some of them toward the other direction, and also I'm making them to start to do their precession in some incoherence. And what happened is that we start to get projection of this vector toward the xy space. So now we had a vector in the z direction. I can flip it all the way or flip it partly. Okay, and while I'm doing that, and they are all coherently moved together, we start to project toward the xy plane. There is a projection of this vector, magnetic vector. It was projected in the beginning toward the z. Actually, it was always projecting a little bit toward the xy, but now as I'm inserting the energy, I'm making them also to move in. I will show a movie in a second. They start to move in or process in a coherent way, and so they sum up, and we have some projection to the xy plane. They move along the xy plane. Okay, so just that's the manipulation. So I can give different amount of energy. Okay, let's say I can use my radio frequency transmitter for long time or short time, and that will change the amount of the projection that I'm going to get. So that's something called also flip angle. What is the flip angle that I'm going to use? How much I'm going to flip this vector? And it could be 10% or 90%, or I can flip them all over 180%. And that's a function of the amount of energy that I'm transmitting, or the duration of this energy that I'm transmitting. So if I would ask myself where I'm getting the maximal signal on the xy plane, in what of this flip angle? 90. The 90. 90 took all the maximum, is taking this vector, and you have a maximal projection to the xy plane. I will show you in a second that we can only measure in xy plane. So that's why I'm asking. And where is the minimal? In the 180. Although in terms of energy, that was the maximal. So maximal penetration of energy will be 180, 90 will be half, if you want. In terms of SNR, signal to noise, in here we have the maximal signal in this point in time. Okay? And there is typically, people, when we're doing this and we have to, it's true that we can inject our radio frequency, but if we do it too much, the tissues start to get heated. There is always a trade-off in MRI experiment between SNR, signal to noise, to SAR. That's the level of energy that we put in, or that might, so that's the level of energy that will heat the tissue by 1 degree. So that's something that we always try to balance between signal to noise to risking the tissue by heating it. Any other questions?
Which one of these is the case of anti-parallel, which we talked about earlier?
So, right. So, when you put them inside the magnet, they will be in many orientation actually. There will be more that will project toward the parallel orientation. That's where we start. As I'm heating the system, I'm taking this. So there is a difference between the one which are parallel and anti-parallel, and I can push it to take those which were parallel, which was the advantage orientation, and take a subset of them, and actually point them to the anti-parallel, and that's my vector. So I'm never working with all the protons, but I'm working with a bunch, and there is more that are parallel. So I'm playing with. So they're creating the vector that I'm going to measure, and they're going to flip to the anti-parallel. Okay, that was helpful. Here is one. This vector is fully projecting to the anti-parallel direction. that.
Sometimes we have a little bit of
Yeah,
the...
a little bit will happen when this effect is cancelled, and we have only the projection to xy, because I flip enough to cancel the one that projects up and the one to project down. So there is no difference anymore between the levels, but they're still incoherent, so they now project on the xy. So here is the video of this magnetic moment processing along the magnetic field. Okay, and you see there is a little bit of it has some projection toward to the other plane. Okay, and it's a vector. It has a size. There is a ratio of processing. This is the Larmor frequency. Yeah. And in the next step, what I told you is that we're gonna excite. So we're adding another pulse. And this pulse, actually, I didn't talk about it, and I'm not going to. It's actually also moving in space. What happened is that now this is the excitation, and so I'm pushing the vector, if you want, toward the xy plane. There is more and more that are now projected toward the xy plane, and that will be useful for us for a measurement soon. Okay. And so let's check your physics for a second. So there is a vector that is now moving and have some kind of projection on the xy plane. What can I do with it? How can I measure it? We have a magnetic vector that is moving in space. How electricity is manufactured, do you know? How electricity is manufactured sometimes. What we are doing with moving two big magnets, and that create what? Current. Okay, so if you have a magnetic vector that's moving in space, what do you need? You need a receiver, some kind of electrical receiver that will essentially see this magnetic vector move, and that will generate a current in it. Okay, so that will be our measurement. So here it is. Here's our projection of the magnetic field toward the xy plane, and soon there will be here a receiver, and there is a signal, and it's oscillate because it go through it and then left and go. Okay, so we have now electrical measurement of this magnetic field that came from the protons in the water in the brain. Okay, something like that. So that's just saying the same. There is this electrical circuit, and while the vector is moving toward it's creating electric current that we can measure. Okay? Any question? And so what we typically have in MRI, we have a receiver. So besides having some machine that do the excitation, that's called the body coil or the excite coil, something that creates the RF frequency, there is something that measure electric current that is emitted outside of our brain from this magnetic. Essentially, it's this magnetic vector that moves, and that can initiate this electric current. And so we typically lie with our brain inside or our head inside a receiver. There is a complex organization of this receiver to get a better signal or measure it faster. So in here you can see that there are several receivers around us. Okay, but we're lying typically in the magnet in our head inside a coil, and this coil called a head coil, which is a set of receivers that will in the end measure this current. Okay. So in general, what is the process? We had spin. They were randomly oriented because they didn't care. They didn't have any magnetic field around them. Then we put them inside the magnetic field. They were aligned together, or some of them at least, enough of them to generate a magnetic vector toward the z direction. Then we excite them with some energy, RF frequency. And so now there is a projection to the xy plane, and we have a receiver that's measuring that. And now I'm going to add one more thing. What happened to a system which we take it out of balance? If we stop the excitation, what will happen after some time? It will go back, right? It will go back. So that we call this phenomena relaxation. That's another important term, relaxation. So we did excitation, We project some of them to the xy plane, the vector to the xy plane, and then you're going to go back. It will take some time, but after some time, in the order of seconds, they will all go back.
Do we measure only the relaxation or also the excitation?
We measure only the relaxation. There is more than one relaxation, and I'm going to dwell on that now. But we're measuring only the relaxation. You cannot measure during the excitation. It's like all the system measure after. Okay, so relaxation. Okay, so here's the experiment of Bloch and Parcel, which also got Nobel. So there are several Nobels on this system. I told you before the system on at least there are many Nobel laureates in this system. They got it for the physics, so they were actually doing NMR. But afterwards, it was also for the encoding of space and so on. This machine, with its own complexity, have many beautiful innovation while discovering the physics of it and then the usage of it. Okay, so Bloch and Parcel, they were doing this experiment. They put a bath of water inside a magnetic field. Okay, that's what it represents. This image. Okay, so here's the bucket of water, and then we sometimes, so this B0 should be, say B, it should be B0. We call the excitation something B1. Okay, this other this excitation that we're using. So for some time, so this is time. They open the excitation, right? They transfer radio frequency to the system, and then they use a receiver. So they listen to what would happen now. They put a receiver near the system, and they found this. They found that it's starting in. They find a signal going up and then going down as we expect, and then it's dying. Going up, going down, going up, going down, going down, gone. Fine. So what was happening here? We just mentioned it. That's relaxing, right? The system relaxed. They took it out. So if there were no relaxation, that's how I showed you before in the movie. They was just going up and down, up and down, up and down. But since they use excitation and then open the receiver afterward, and they wait and wait and wait, that's what it symbols. The thing will keep oscillating, but until they get to their noise level and they cannot measure anymore. The signal is gone. Okay. So what we're gonna do? Time passed fast. So what we're gonna do is describing the two main phenomena of relaxation. There's two main phenomena. One called longitudinal relaxation, and the other called transverse relaxation. Okay. And there are two competing phenomena that happens in this experiment. And let me just check. Yeah, let me do the longitudinal relaxation now. So what happened in here in this experiment, or what we can think of, we had a vector. We excited. Let's think we did a full 180. Okay, right to the other direction. And so what would happen to this vector as it relaxes? It will go back. It will go back, and that will take time. So if we take measurement in different points, we'll find it in the beginning projecting down, and then slightly less. Right? It will be smaller and smaller, and then smaller, but to the other direction, and then toward the end it will just go up. And that takes some time, and we can use a mathematical equation to describe this relaxation. It happens to be an exponential relaxation. Okay, so we can find an exponential relaxation. We're going to give it some time constant. We're going to call it T1 because it's the first one. The longitudinal relaxation is the first one we're going to discuss. T1, the longitudinal relaxation. Let's have a time constant. These time constants have values which are somewhere between 4 seconds for water in body temperature, so that's what we find in the ventricles, for instance, in the brain, to about 1 second for the brain, for brain tissue. And that's actually going to be very useful. I will discuss it in the next class. So we can measure the relaxation in the brain. It's going to be in the order of seconds. And just to give you some kind of intuition of what's going on in here, Bloomberg and Parcel this model which is called the BVP theory, which tried to explain why the relaxation change for water, just in water versus water near things. Tissue is a thing, macromolecules. And apparently the relaxation has to do with that. So these protons need to give the energy that they have right now to the lattice, to the environment. Okay? And so that has to do with how much they move, tremble and change their positions. And when it's only water near water, the chance to find someone to take the right amount of energy, remember it's a quantum phenomenon in the end, is very low. So it takes very long. 5 seconds is like forever for an experiment. While when there is macromolecules around them, lipids, proteins, things like that, water kind of stop for a second, for a picosecond. Second is wrong here. Stop for a really short time, and that accelerates the chance for them to release their energy. And so we have relaxation. So that's why we have a different. So this is the tumbling of those molecules of the water, and it's the chance to find the right tumbling or right amount of energy of if you want movement that will fit the relaxation is really low if they only see water, but if they see other things, the chance for that is growing. And that's why we have a different relaxation between water and tissue, and there is variability within tissue. That's actually important. Okay, now let's take a break, and we're going to continue with transverse relaxation in the next hour. Super happy here. Should we No. Yeah, más que no se puso.
מגניב, לא חסים עליהם.
Okay. Okay. So next, now, we're going to talk about the transverse magnetization. That's the other phenomena, the second phenomena. And actually, it's faster than the first one, the longitudinal. So we're going to call this one T2 because it also will have a exponential relaxation. The second one, so it's T2. And here is the following. When this has to do with the phase of those protons in the XY plane. So if you remember in the longitudinal, we took them to the minus Z and they went back. And as we did that, we said that there was some kind of a vector that would project to the XY plane. And I told you that they are incoherent. They all project to the same place in XY, or enough projecting the same location in XY, so we can measure a vector that moves in XY. What would happen is, so of course, before we start, there is nothing. There is no coherence. They are not in coherence, and they cancel each other. So as we excite, so no signal in the beginning, right? As we excite, there is enough protons that are coherently projecting to the same location, and so they move. So we can sum them as a vector, and that's the vector that we saw moving before. As time goes, even before the spin themselves go back to the Z direction, they get out of phase. Okay, so from our perspective, they're lost. We cannot see them anymore. So as time passes, right, this vector is going to move. It's moving, but also shrinking. And it's shrinking because in the beginning they were all coherent, and as we move, you see these ones get out of coherence and even more. And so as they get out of coherence, we lose them. We cannot measure. They cancel each other. So lose coherence means no signal. So when they totally out of coherence, there is no signal for us to measure, even though they didn't go back yet. Okay? Or not enough. Not all of them went back in terms of T1. So this is called T2 phenomena. And it's also an exponential. That's why it's the same. It's described by an exponent. It's an exponent, time decay T2, always faster than T1. Okay, so if we will have a movie of that, here is the pulse. I will run it again. So that was the vector, and as they went out of coherence, the signal decayed. Okay, let's rerun it. Again, nope. Here it is. Vector is decaying in XY because the spin getting out of phase, and so our electrical signal that we measure decay. That was the T2. Fine. So this is the phenomena. Why would they get out of coherence? What do you think? You can just speculate. Play with me a little bit. No?
They're going back
they're
going
not
back.
at their original orientation, but they're going back to their.
So the going back itself, you think, gonna make that? But actually true in a way, because what happens is that each of them experience slightly different magnetic field. The fact that your neighbor might be in spin up or spin down mean that he creates some kind of a perturbation in the magnetic field. So any local perturbation in the magnetic field will make them experience slightly different magnetic field. Slightly different. I think this magnetic field, slightly different frequency. As time passes, you lose coherence. Okay, yes, if you want, your alarm frequency is slightly different. You get out of phase. It looks like that you get out of phase, like they're not coherently move together anymore. Okay, and so this effect is called spin-spin interaction. The fact that you have near you other spins, which each of them move slightly different, have a slightly different relaxation. Okay, all of that is going to create some small perturbation in the magnetic field, which take them out of coherence from their neighbors, and so they not sum up anymore to be one vector. In the end, they will cancel each other. Okay, so this is the spin-spin interaction. The other effect is that if there is by any chance some kind of inhomogeneity in space, if actually the spin in here feels slightly different magnetic field, or not like different magnetic field, then the spin just nearby them. Say there is some kind of inhomogeneity in the magnetic field. Let's say the B0 is not constant, or there is maybe iron in there that will create some kind of perturbation in the magnetic field. Anything which is inhomogeneity in the magnetic field will make them dephase, just make them dephase faster. Okay? So any kind of gradient in space, remember the name gradient? So any local field inhomogeneity will also cause for this T2. So we have two phenomena that create a T2 relaxation. We're going to call it T2 star, and it is the sum of the T2, which is the spin-spin decay, and the T2 tag, which is the inhomogeneity in space. Both things creating some kind of, if you want, local inhomogeneity, but from different source. Either it's your neighbors, your friend's spins, or it's like the environment, something in the environment. And in both cases, this will create to decay of the signal, dephasing and decay. Okay? So this is going to be T2 star. And just remember that this T2 tag, we can actually create it, deliberately create it using gradients. We're going to do that. I don't know if I'm going to get to that, but we can do it. Okay? We can actually create it and take it off. And also, another important thing about it is that I said already iron, but also oxygen deoxyhemoglobin, which we have in our blood. One of them is paramagnetic, the other one is diamagnetic. So when we're going to talk about functional fMRI, we're going to talk about this magnetic field perturbation due to the blood oxygenation level. So the fact that the neurons now consume energy or not, changing the level of oxygen deoxyhemoglobin in the blood, that creates perturbation in the MR field, which is a signal that we can measure. That's fMRI. That's functional MRI. So this very physical phenomena that seems like to be related to nothing will be the thing that will be used to functional MRI in 3 weeks. Okay? Anyway, so now you're getting into the idea of the measurement or the phenomena. Now we need to find ways to measure them. Just a summary is a T1 relaxation and a T2 relaxation. We actually describe it as two phenomena, and we also say that this transverse T2 phenomena is faster. This is just a summary. Let's do one more summary thing. Actually, now I want some of you to describe this. So I start with that. A few slides ago, and someone just describe it in what's going on in here. What this cartoon thing shows. Who want to try? What happened first? What happened first?
Yay. We create a magnetic field.
Yeah,
which is uniform to the B0 direction.
Yeah.
Which is in that direction.
Yeah, and we put some water, some substrate, which have many hydrogen protons, which are. And then what happened? Someone else want to try?
Inject a radio frequency.
Great. We inject. Yeah.
And we measure with the receiver the current that's
Let's split it to two. What's the receiver? What you said we inject radio frequency pulse, and that's mean what for this, in terms of this vector? What happened? I want to say
Excitation.
excitation. What do you mean? What do you mean by that?
That the vector sound of X is aligned to the XY plane.
Yes.
That means
How? Because we
because there's the parallel, maybe
Par-
anti-parallel.
yes, right.
In the preferred is the parallel, and we
Make them jump from one level to another,
them
and they were coherent as well. You remember that? And that's what created the XYZ projections of this vector. Okay. So now there is receiver. Who want to say what's going on with the receiver? That's right.
We measure we put the system in a higher energy state, right? And the energy is released by an electrical current because it's a moving magnetic field.
So there is a moving magnetic field, and there is a receiver which can measure it, right? Okay.
Measure the current that
Okay. Right. And then when we measure it, so that explains this oscillation. But then we also see another thing. Who want to explain that? Should I choose again?
We see a decay in the signal
Okay.
as the magnetic field returns to its previous state.
Okay. So as the magnetic field, not the magnetic field, but the magnetic vector going back, and it's actually going back. Or what do you think is going on in here?
It's moving closer and
Which
closer.
we talked about two relaxation mechanisms. Remember? Which one was faster? The transverse. So what's happening here is actually we're losing the signal because of the transverse relaxation. Okay. Okay. So now you know. Fine. And then here is another question. So here's the signal when I'm using one pulse. Here's the signal when I'm using another pulse. And this is what happened when I use even stronger pulse. So who want to say what's going on in here? But yes, but someone else maybe, because you already did. Who can? Any intuition, something about what's happening here?
Maybe it's going more high.
Well, so you also answered already. Someone else? Just say it again.
maybe it cancels out
So where it cancels out?
when like
What do you mean? So what is the difference between here and here? You can,
so the amplitude is bigger.
in here,
Yeah.
because probably what happened?
Probably like the excitation is like
If say is greater, and then we get what kind of angle maybe?
we get the 100.
So this is 190, you think?
No, not this one. This one is the 90.
Yeah.
And this one is the 100.
Exactly. So this is full excitation. If you want to take us to 180, we have nothing in the XY plane right now. But in here, we in the 90, we have a signal to measure, right? And the maximum signal. Here it's probably lower angle. Okay. Exactly right. And that's where it should have been the break. Fine. So now what I want to do is talk with you a little bit about pulses, MR pulses. And that's what we're actually doing. So this is a little bit of practicality of how we're actually measuring the different phenomena, T1, T2, T2 star, at least making an image which is sensitive to T1, to T2, to T2 star. It will make a big difference for us in our experiment if we want to do fMRI or anatomy. So we need to find a way to measure these different phenomena separately. Okay, so this is an actually very interesting experiment that happened by mistake for Han in 49. He was doing this free induction decay experiment that you already know, right? Doing the normal the experiment I showed you before, which you know to explain, called free induction decay. We gave a 90, and then the signal dies as a function of time. That's free induction decay. Okay, it decaying in time freely. Now he kind of by mistake say, let's turn the excitation coil again after some time. He did here a 180, and suddenly we turn it in here, so when there is nothing. Okay, you see 90 for induction intake, then he turned the 180, and then suddenly after like there is some time here, let's call it half time or something, then in exactly the same time afterwards, he suddenly finds a signal. Signal suddenly comes up and goes down. And so there is an echo. And so the time between those two things called TE, time of echo, and in this sequence called spin echo. Okay, and there is a signal equation for it, which is we can show it only sensitive to T2. I will try to explain what's going on now. Okay. So what is the intuition of what's happening here? Think about, so there was a 90 and there were, what was happening is that things start to get off. There were different spins. Each of them get off, were head on, if you're on a frequency a little bit, and that's where we got dephasing, right? So, and then what happened is that he pushed them to flip them to the other side. They were in the 90, he flipped them to the minus 90. So now they're going to dephase again, but just in the opposite direction. So there will be again a moment in which they be again in phase. So after some time, I'm going to show a movie for that. But essentially, those ones, if you want, went far, get out, they're on slightly faster frequency. Those ones have a slower frequency. They're out of phase now. But as you do this 180, you can say to them, go back, start to dephase, but in the other direction. There will be a moment in which there will be a line again, and we're going to see an echo. Okay? And so this is the movie of that. So they dephase, and then you flip them, and then there will be a moment in which they are in echo, and then they die, they're almost dead. They will be here 180, and so they're going to rephase again. And, I want that. Kind of a hard thing to do with this one.
I don't understand exactly. So he injected a second, like, rated frequency?
Yes.
Flip it?
Yeah, this is the 180. If you would see here for a second, there will be also a curve that was fitted along these lines, along the center. I cannot pose it in this one. I don't know why. It's going to come in a second. This one, this red thing. And so if you go from peak to peak to peak to peak, the only effect that's left, right? So if there is any inhomogeneity in space, they kind of like they went back. We cancel it by make them if you want do this 180. But the only thing that's not gonna be come back is the spin-spin interaction. We cannot cancel that. So all the decay that we are seeing is due to T2. So that's why it's a way to measure T2. So spin echo is a way to measure T2 because we kind of like removing the effect of T2 star or T2 tag and staying only with the T2. The effect that comes from the T2 effect, this flipping the spin with 180 cannot cancel that. That's lost. What lost in spin. And so we have a measurement which is T2 dependent. Now, let's say I really want to measure T1. Yes.
I don't think I really understand.
It's painful.
The spectrum is here, and then we turn it into 90 degrees, and then
And it starts to lose it.
180.
Start to lose it, right?
Yeah.
So there is some kind of a radiant in space, and some of them which are here can start to dephase faster and slower. And then when we flip it, now they're gonna again dephase faster than those ones, but it's gonna be for the other direction. So there will be a moment because the vector is now flipped in the other direction that they will be again in phase. And so you get an echo, and this echo is essentially you see the vector again. You see them again, like they're all in the same phase for a moment, beside the effect that came from T2, spin to spin interaction. This one is gone. This one is done. There's also effect of T1, which I am ignoring right now, because it's much slower than this T2 effect. Okay, so, but if I really want to measure the T1 effect, what should I do? I wouldn't know to answer that. But you can make another manipulation. Let's say I would add another 180 in front of the spin echo. So before the 90 and 180, that's our signal, right? To create an echo, I would add another 180. So this 180, just turn them all to be in the -z, right? That makes no difference, besides if I'm waiting some time. It's called inversion time, TI or IT. Why does it make a difference? Because if let's say I will flip them to 180 and wait exactly the time for them to be exactly in 0, 0. So there's no projection on Z anymore. They all went exactly half. Then I can do a 90, but there's nothing to flip into 90 because the vector is exactly on 0, right? It's going down and go up. It's the T1 effect, right? So changing this time will make the vector that I'm working with in different size, depending on what was the time between the 180 to the 90. So that make a measurement which is sensitive to T1. Okay? I know it's hard. So there was a vector, then I'm doing the 180, and if I'm waiting longer, I can do now the 90, I will get the full vector, right? If I wait some time, that might shrink. And so when I will do this, now I will do the 90, it will be smaller. And if I wait even longer, it might be just the same or smaller, depending where am I in its way to go up. So doing this with different times will give me a curve with the x-axis is inversion time, which look like the T1. And that's what we're doing. Fine. I know it's hard. Questions? To actually understand it, what I'm suggesting is to look at that afterwards. Because otherwise it's a little bit hard. We need to think where the vectors are in fraction of time and so on. But you can have a look, and then you would see that the intuition is not so hard, actually. Just playing with the time before we starting the spin echo experiment. And this time change the size of the vector, which the size of the vector is T1. Is how long it takes it to go from being 180 to go back.
That depends on the tissue?
Yes, but all this dependency of the tissue in next week. Yes, very depending on the tissue. Different tissue will have different T1, different T2, and we'll be excited about that, and we'll be able to measure things about the brain. So otherwise we wouldn't care, right? Like, fine. So I have some time. Do you want to ask question? Otherwise, I'm going to move to something which is even more painful, which is how you decode space.
Can you say why we need another 180 after the 90?
So that's for the spin echo, right? So this is doing a spin echo here. That's the echo.
Right.
So that was a spin echo experiment, normal spin echo experiment. And now with the 180 in front, it's make it a spin echo which is depend on the time between the 180 and 90. That becomes sensitive to T1. Okay. So now we're going to talk about coding space. And if you remember, that happened with these gradients in space. And so what gradients do, they're creating small perturbation in the magnetic field. Okay? So we already know that if we have a gradient, some kind of like inhomogeneity in the magnetic field, the spin will dephase in a slightly different rate, right? That's what we saw before in the T2 star effect. So we're going to use this phenomena with those gradients. No, actually I had another sequence. The gradient echo. I might just skip it. It's the least intuitive. I'm going to skip spin echo. Skip it. I just would say that there is another manipulation which allows us to measure T2 star and not T2. Okay? Playing again, doing the same spin echo experiment but without the 180, still getting an echo. There is a way, creating using the gradient, creating dephasing, and then rephasing. That's creating another echo. Right? I'm taking them out of phase, and then using just the opposite gradient, I'm bringing them back to phase, the one that's there. And that's creating an echo, which is very useful to measure the T2 star. Okay, important for me is that you know that we can do these games and then be sensitive to different contrast mechanisms, different relaxation mechanisms, T1, T2, T2 star. They're all happening, but we have a way to be sensitive to one versus another using these manipulations. Okay, now decoding space. So the interesting thing about decoding the space in MRI, because we're going to get in the end some images. This is a T1 image, by the way, and you might see in this image just by looking that the white matter is kind of brighter than the gray matter, and the ventricle is even darker. This is all mostly due to T1 phenomena that we mentioned before. We're going to talk about it much more later, but that's in the end the image. But until now, all the things I was saying was the notion is there was one voxel, one thing that we measure, either T1, T2 in one location. Now I want to do it everywhere. That's going to be very hard. And the interesting and even more complicated thing about it that actually we're not going to measure an image. We're going to measure it in a different space, what we call K space, essentially the Fourier space. This image, everybody did Fourier, right? Okay. So this is a second order 2D Fourier. Okay. So this is we're going to explain what it is exactly, but we actually measure in this space, and only afterwards we're going to do the inverse of the Fourier and create an image. Fine. So all the measurement is going to be here. There was another Nobel for that. Okay. So what is the problem? Again, let's say we have two beakers in our uniform magnetic field, right? And so they have their own each of them. So this is the magnetic field. They all feel the same magnetic field, and so they have one oscillation, one theta, one Larmor frequency for all of them. So I have no way to separate between them. I don't know. I put one beaker, two beaker. I have nothing. I don't have a way to say if I'm measuring from here or from here. Okay, think about this: two voxels we call them, or two pixels in the image. In MRI we call them voxels because it's a pixel with a volume, so it's a voxel. I have two pixels, and there is no way to separate between them currently. And now, if I will create some kind of perturbation in the magnetic field, so this beaker is going to feel one magnetic field, and this one will feel a slightly different magnetic field. That means that each of them has its own Larmor frequency. They will oscillate in slightly different frequency. Okay? And so if we think about it as two time series, right? You remember we're measuring time series. We have two time series, and we're going to measure the sum of them. Right? Before they had the same one, we just had the same time series twice. Maybe we had bigger amplitude, but they were exactly the same. Now, if I'm going to sum those two, and I'm going to do that with the gradient, right? This effect, I'm going to get some complex time series, right? So I have two frequencies in it. So what should I do now in order to see it easily? Fourier, right? So easy in 1D. What happened? Oh, in 1D, we have two frequencies. Each of them have its own amplitude, and we're good. We have a way to decode each position. Good. So in 2D, so you know already. You told me you know that any kind of time series we can decode using Fourier transform using this equation, which have amplitude and phase and frequency, right? We're going to put weight on those, and we're going to get our time series. And in 2D, it's kind of the same. Did you see 2D Fourier, or that's the first time? Okay, let's do it. It's kind of intuition. Did Udi teach you? Udi already did in physiology. He actually talked about that. I saw his video. It's actually, you will see that you might recognize it. So I can make this 2D images, if you want, which have different frequency. Okay, so instead of 1D, now it's 2D, and I can talk about kx and ky, 2 dimensions. Okay, and I can talk about the rate, the cycle, like a frequency in 1D. Right. So now I have like these images, these wave cycles, and they might have a higher or lower frequency. That's in just kx, right? Or they might have a frequency in the other dimension, or some kind of a mixture of those. Okay, so I can create a base of those 2D images, if you want, which I can identify with kx and ky, right? So those frequencies, very similar to what happened in the 1D case, just in 2D. And then I can sum them together, and then we can create any kind of image. Okay, so very similar to what we said in 1D, we can say now in 2D. Actually, we can extend it to 3D as well, but it's enough in 2D. So here is the movie I stole from Mickey Lustig that you saw his talk. This is his work. He's working only on that, on how you play with this thing. So what happened in here? Here is the amplitude of different frequencies or different waveforms, and as we add them, we start with the low frequencies and we go out and become higher frequencies. As we add them, we're getting an image. Okay, so that's essentially the Fourier transform from the frequency space, for the K space we call it, because it's X and Y, to the image space. Okay, we're adding these boring images which have these cycles, and we add them in different weight and different, right? And again, it could be in many orientation, and summing them together can bring us the image. And so in each image we have low frequencies and high frequencies that generate the image. We just need to sum enough to get an image that we can recognize. Fine. So each point in K space, again, I'm just saying the same thing. It's this kind of 2D description of a frequency, right? And we need them all. We need the weight of each of them in order to generate an image. Sure. And if we will, let's take an image. We take the full K space. We have an image. If we take only the center of K space, that will be only the low frequencies. So we get a low frequency image. Let's say we just wash away the low frequency. We're going to say just with the high frequency aspect of the image. Can you see that? Just the thing that changed fast, and here is the thing that changed slow in space. Are you with me? Good. So now we're going to use this phenomena, and one thing we're going to do even before using this phenomena, we're going to say, okay, let's just first select a slide that we want to work on. Here is a magnetic field. We're going to create a gradient. This gradient says that there is for each slice, for each location in space, we do it in one orientation. There is a particular frequency that will excite it. Okay, you remember we have to excite in the frequency of those protons according to the Lamor frequency. If we create this gradient, the one here has a different characteristic frequency than those in here. So by putting this gradient before excitation, and exciting only in one or subset of a narrower window of frequencies, I'm kind of selecting an area in the image, area in the brain, area in the volume. Okay, so that's creating a slice. Okay, so if I had a 3-dimension problem, I'm just by that making the two-dimension problem. Still, all of them are stuck together, and I don't know how to separate them apart yet. But by that, I just made a 3D problem to a 2D problem. Before excitation, I put a gradient. And so when I'm exciting in specific frequency, only this side is going to be excited. Are you okay with that? That was clear? Yes? You're very quiet. I don't know. Yes. Okay.
For each slice, we get this map from the Fourier, and then we can plot it.
Yeah. Well, first select the slide, and now we're going to do the 2D Fourier. So I moved 3D problem to 2D problem. Still have a 2D problem. Now I'm going to do all these things with K space. Okay? Okay, it's just a movie that's showing that. Selecting first using a gradient, and then we're only exciting those spins in this slice. That's what it says in here. Fine. So let's kind of stop selecting from the 3D problem to a 2D problem. Okay. So now I'm going to also use gradients, and what would happen is that the spins in my 2D plane, as function of time, I'm opening the gradient, they're going to kind of aggregate a phase. So now each of them looks slightly different. In this case, they're creating phase in the x direction, and in here in the y direction. So in each point in time, there is some kind of like the signal is a summary of spins, which some of them orient here, some of them orient there, depend of where they are in relation to this x gradient and y gradient. Okay, so I'm kind of like I took them all from phase. So now each position has its own x phase and y phase, and that changes function of time, right? As I'm waiting, they getting farther away from each other. And in the beginning, they all kind of were aligned. Start to lose it. Again, I'm doing it in the x dimension and the y dimension. Fine. And so you may think that now actually I have everything, right? I had the slice direction, and now for each point in time, I can tag it according to the x gradient and y gradient. I have everything to measure point by point. Say, oh, if you have exactly this phase in x and exactly this phase in y, or can I say what should be the phase for this position according to what the kind of gradient I use in x and the time, and the kind of gradient I use in y and time with that path, and say, oh, this is the signal coming from there. But actually, that's not the way. We're not going to measure x, y, z in that sense. We're going to measure in k-space. So let's see how that goes. Okay. The information is here. That you might notice that I have enough information. I decode x, y, and z. But I'm not going to measure it in like let's measure point by point. Okay, that's going to take very long. Let's do something else. Okay. So as you remember, in k-space, each point relates to all the image. It just relates to specific frequency in the image, right? Spatial frequency in the image. Right. This is maybe the mean, but each point it represents some frequency, spatial frequency in the whole image. And so I'm gonna use that. Yeah. So what if I had a uniform objective? I'm gonna make this problem now a 1D problem, just to understand it. Say I had a uniform object, and I use no gradients at all. They are all aligned, and I'm getting the maximal signal, right? But let's say, what would happen if I would use a gradient and they start to get out of phase? I'm going to lose signal because they're going to start to cancel each other. Let's say I use a gradient, and after some time, right, as a function of time, they start to create this kind of like this kind of shape, which they go fully out of phase and even further and further. So they gaining phase as function of the gradient that was turned on. And so what would happen in this case for this object is that they're all going to cancel. If I'm summing up, they're all going to be canceled. I'm going to get zero signal. But what would happen if my object will be different? It will look like that. It will have some kind of frequency in it. So from here there is proton, here there is nothing, here there are protons, there is nothing. Let's say the tissue bond, something like that. Like I'm exaggerating, there's nothing like that. But if there is this kind of frequency in my object, then it's not going to cancel out. And I'm going to get a signal here, right? So I'm going to get one type of signal from here and a different type of signal from here, because there will be some frequencies or some spin that are not going to be cancelled. Okay, so I'm going to get an object, or I'm going to get a weight for this frequency. So I can say how much signal do I have, and this is essentially the weight of this frequency in my object. Okay, that was okay. That's the whole essence. what it is. And so as I'm waiting different time, I'm essentially changing how much they're getting out of phase. So what kind of frequency I'm actually sensitive to, different time, different frequencies. And each time I'm going to get a signal. This signal is going to be the weight of this frequency in space in the object. Some nodding. Everybody feel okay with what I said? It's the most hard, for me, it's the hardest concept. For many, actually, in the field. It's a kind of, you want me to say it again, or maybe you want to ask a question? It's not simple.
I'm not sure what I understood. What's the difference between a uniform object and
Okay.
why would it cause a difference?
Let's say we have no gradient. Measuring the uniform object, they all oriented in the same direction, you get the maximal signal. Let's say I'm using this uniform object again, but now I also use a gradient which creates them to get out of phase. I use it enough so it happens 3 times, okay, along this direction. So what would happen now is that, and now I'm going to measure the signal as a function of time, right? In this position in time, I'm essentially sensitive to this frequency, like something that on, off in this frequency. Okay, in this uniform object, there is nothing of that. So all of them are going to contribute. Every position is going to contribute spins. And so what would happen? This guy going to be cancelled with this guy, and this guy going to be cancelled with this guy, and so on. And so essentially, what would happen is that they came from here. All of them exist, and this frequency doesn't exist in the image. And so the sum of the signal from those spins is 0. But if I had a non-uniform object, which has some frequency in it, there is a typical frequency for this object. Yeah? I don't know. Signal, no signal, signal, no signal. It's exaggerating. They say yes and no, right? It's never binary. But there is more contribution from here than in here. So those are going to contribute, and they're not going to cancel for something. There is nothing that's going to cancel them. So in this frequency, it's again going to be in the same phase. And these ones, they don't exist. They're not contributing, and also not contributing. Or cancelled by nothing. Nothing is nothing. So they only contribute, and nothing is going to cancel them. And so I'm going to get a maximal signal with this frequency. If I would make more time, and it might be in a higher frequency, I might lose it again, or not going to get a maximal signal. As a function of time, this cylinder will, or this the orientation of those spin, the spring will change this. I will create spring in different frequency, and so I will be sensitive to different frequencies in the object. And that's the whole idea. Okay, so each time I'm measuring a point in time, I'm actually measuring frequency in the object. And this is basically it. So we have a time series, right, that we measure, but it's actually the weight of the different frequencies in K space. That's the thought. So I'm measuring this line in K space, this line in K space. It's called line in K space, position in K space. Measuring different positions in K space. I have the weight on that, weight on that, weight on that. I have different weights for different positions in K space. And now when I have the weight of all the position in K space, I can do the Fourier, say, oh, this is the image.
When you say weight, do you mean
the amplitude? Yes, yeah. It's amazing that it's actually working. But it is. So what people then do, then there is a question of time. I'm just going to tell you something about the reality of scanning now. Measuring all the position in K space, it still takes time. And if we take the full image, it takes very long. We need all the position. We have the amplitude of each position in K space. We can generate the image. Let's say we take only the center. We're going to get a low frequency image. That's what happens. I don't have enough time. You take less. You get a blurry image. Sometime we're going to sample subset of the frequencies. Let's say we subset them in some kind of uniform way. What would happen is we're going to get aliasing. When you talk about Fourier, maybe talked about aliasing. Maybe not. You lose the special. Well, things start to like flip on each other. There's two things that can be, both of them. Not gonna explain aliasing. But if you don't have enough frequencies, you cannot explain all the higher frequencies, and then higher frequencies and low frequencies are mapped to the same position, and you get this aliasing. Two phenomena on the same coefficient, which would create this aliasing in the image as well. Now, okay, so it's a typical sequence in MRI, and this is really the end, and just give you the feeling of just how it goes. We turn in the X and Y, and we do it, so that takes us to a position in the K space, so we create this amount of phase in X, this amount of phase in Y, and maybe then we're going to do some 180 that will flip us to another position in K space, and then we're going to start to listen and listen and listen, and as we listen, we're filling the line in K space. Okay? That's what we get the signal. I told it before, but as we wait, we get it generating more and more the spring changing its position, and we kind of measuring different line in K space. That's what we think. We get the wait for different lines in K space, and sometimes we really want to be. This is very slow. This takes forever to scan an image like that. So what we do typically, we're doing different things that make it faster. So a way to run fast along the K space. I did that already. Here it is. And so what we're going to do, we're going to turn on and off, on and off, on and off very fast the gradient. That's what makes the noise in the end. Da 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 da. It's this. This the gradient turning on and off. This electrical currents. If you've been in a scanner, you heard the noise. It's this. We're putting a current, creating a gradient, closes it off. Da da da. It's actually banging. The metal is banging what it hold it, and that creates the noise. And then that would allow us to move fast within K space, to essentially sample K space faster. We're not going to sample all the points, but we're going to sample many. So this is this red point. So this closing on and off, allows us to run fast through K space. It's not the full K space, but it's a good sample of the full space K space. That's a way to create a fast imaging technique. That's like a big push in MR engineering, is how to measure it fast enough. That's the struggle that we always have. And there are many ways people are inventing many ways to go in K space. Sample K space, spiral, EPI, other things. And people using many things about Fourier space that we know, that there is symmetry in Fourier space. So maybe we don't need the full K space, the full Fourier space. We take some of it, and then we say, oh, there is symmetry. We're just going to project. And by that, so essentially that's kind of like that. All of those things are a way to kind of, if you want, I lost the word. Well, it's way to it's like JPEG, right? In JPEG we have a full image, but we actually don't use the compress. It's a compressed sensing approach. You heard that compressed sensing? The word compressed sensing. The idea in compressed sensing is that I'm going to only measure a subset of my image, or subset of my space, in this case K space, and in some way I would use the fact that there is some similarities in here. They are not totally independent. For instance, in K space there is a full similarity. And so if I take, let's say, 60% of K space, I can feel the other part. They're not really independent. I can make a model, something like that. And so I can make a faster measurement, but I need to have some knowledge about how K space behave in order to do that. People do that. And that's it, actually. I will be done. There is other methods. But this is a very big push to make it fast by playing with K space. Thank you. Next class will be more toward the brain.
have like you have the primer slides
Right.
in the presentation.
Right.
So you go first to NVCI website,
Okay.
and then you can find, first you choose the genes.
Okay.
Like
You
just
just looked up genes that are associated with the reward circuitry, isn't it?
yes, let's find like the easiest ones that are like the ones related to the
Okay.
reward
The
circuitry.
genes that mediate dopamine.
Not just them,
Or whatever,
both.
yeah, something.
And then you find them in NVCI,
Okay,
and
let me write
then
this down, sorry.
you can also check in Wikipedia.
Right.
That after you find the specific gene, you find it in the mouse, or
Genes.
like it's written there. It's like muscle.
Right.
The
I saw
letters.
that, I saw,
Yes,
yeah.
and then you check in Wikipedia that it's the same one. How do you check it? You just see the in which chromosome it is
Okay.
and the location, and it's written
And then
in
it's
Wikipedia.
okay.
You have on the side, you see like the geolocation,
Mhm.
and then you choose mouse
Uh-huh.
in Wikipedia, and then
Yeah.
you see like in which chromosome it is, and then after you found it,
And then you put it into
you
the
put it
blast.
in the blast. You have like you have the name
Mhm.
of the mRNA.
Right. Where you from in the Wikipedia?
No, in the NVCI.
Ah,
You just
NVC.
check in the Wikipedia the place that it's the same one,
Okay.
and then you have, I don't remember how it's called. I think it's called איך קוראים ל-mRNA לקיצור היה? NM?
NM ולא NP.
Yeah, you see two names of
Right.
the genes, NM and NP. NP is the protein, so you don't need it, you need the mRNA.
Okay,
So
what
you take name of the mRNA,
Okay.
you put it in the blood, in the prion
Okay.
blood, and then it's like, and then you choose all the conditions from
That they give you?
yes, in the prion blood, and then you like submit it,
And that would just be the
and
sequence.
then you have to wait like 2 to 5 minutes,
Oh wow.
and then you get it,
Yeah?
and that's it.
It was bad or like it took
No, it wasn't bad
So you have to
actually.
find the genes. I mean, it didn't take you too long to figure out which genes are the. That's fine. I think I
No,
get it. I just.
the guilt. No, I remember. I think
Send me that one.
we
Maybe that could be
choose.
good.
I don't.
And Michelle has it. She probably
Alicia
should.
has it.
She just doesn't want to send it to me.
מה?
But just
really?
מה אני רוצה לשלוח לך?
הוא אומר לך דברים רעים
Yeah.
או?
אני לא שלחתי לך עדיין?
No.
הנה אני שולחת לך עכשיו.
I think that's the hard. For me, it's something I wasn't sure how to do that.
אני מאוד נחמדה בסך הכל.
תעשה.
מחר אני יכול לבוא בבוקר? זה יפריע לך אם אני אבקש קצת תיקון באנגלית? אני מאוד רוצה לעבוד בשביל להגיד את
אני אגיד לך מה appropriate
No.
strategy
כן.
is to look at the
זה שלנו, זה הכי טוב.
כן, אבל יותר מזה, אני רוצה לקרוא אחד נורמלי לפני, שאני אבין למה צריך להגיע, כי אני לא מבינה מה צריך להגיע, ואז לפי זה לשנות את מה שאנחנו צריכים.
כן.
זהו.
כן.
אני לא רוצה עכשיו להתחיל לבנות אותו. אני לא מסוגלת לבנות אותו בעצמי.
סבבה, נעשה את זה ביחד אבל.
כן, אז אתה מוזמן לבוא כמה שיותר מוקדם.
אוקיי, אני אבוא ב9.
באמת?
אני...
חשבתי אני אופסייד.
לא, הבנתי שאני חייב, כי יש זמן. Okay, 9 a.m. Welcome to party.
not so
She don't
much
want
time.
to.
No, that's not so much